Cryptography. It sounds like a big, complicated word, doesn't it? But consider this. Have you ever written a secret note to a friend? Maybe you replaced every letter with a number, or you shifted the alphabet by a few letters. If you've done that, then congratulations, you've used cryptography. It's the science, the art really, of writing and solving codes. The main goal is to protect information. We take a normal message, something anyone can read, and we scramble it up. We turn it into a secret message that looks like complete nonsense to anyone who doesn't have the special key to unscramble it. Think of it as a secret language for your computer. The original message, the one you can read, is called plain text. It's just plain, simple text. When we use cryptography to mix it all up, it becomes ciphertext. This ciphertext is what gets sent across the internet or stored on a computer. It's designed to be super tough to read. The process of changing plain text into ciphertext is called encryption. It's like putting your message into a locked box. And the process of changing it back from the jumbled ciphertext to the readable plain text is called decryption. That's like using the correct key to unlock that box and read the message inside. It's a fundamental part of our digital world, working silently behind the scenes. So, how does this scrambling and unscrambling happen? It all comes down to something called an algorithm. An algorithm is just a set of rules, like a recipe for a cake. In cryptography, the algorithm is the recipe for how to mix up the letters and numbers in your message. But a recipe alone isn't enough. You also need the ingredients. In our case, the special ingredient is a key. A key is a piece of information, usually a string of numbers and letters, that makes your encryption unique. Without the right key, trying to read the ciphertext is like trying to bake a cake without knowing the ingredients. It's just not going to work. This amazing science isn't new. People have been using codes and ciphers for thousands of years. Ancient Romans like Julius Caesar used simple ciphers to protect their military messages. If a messenger was captured, the enemy would only find a bunch of gibberish. During wars, spies used incredibly complex codes to send secret information back to their home countries. Today, we use cryptography for almost everything we do online. From sending an email to buying something from a website, cryptography is the guardian that keeps our information safe from prying eyes. It's science in action, and it's happening all around us all the time. So, why go through all this trouble of locking up our messages? Well, think about all the important information you have. Your bank account details, your private conversations with friends, your passwords for different websites, and even your medical records. This is all personal data. You wouldn't want just anyone to be able to see it, would you? That's the main reason we need cryptography privacy. It builds a digital wall around your information, ensuring that only the people you want to see it can actually see it. It's like having curtains on your windows. You get to decide who can look inside. Another huge reason is integrity. How do you know that the message you received is the exact same one that was sent? What if someone intercepted it and changed a few words? Imagine getting an email from your bank that says, your balance is $1,000, but the original message was, your balance is $10,000. That would be a big problem. Cryptography helps ensure data integrity. It can help verify that the message hasn't been tampered with or altered in any way during its journey from the sender to the receiver. It's a digital seal of approval that says, this message is authentic and unchanged. Then there's authentication. This is a fancy word for proving that someone is who they say they are. When you log into your email, you type a password. That's a simple form of authentication. Cryptography takes this to a whole new level. It can be used to create digital signatures, which are like handwritten signatures, but for the online world. They prove that a message came from a specific person and not an imposter trying to trick you. This is incredibly important for things like online banking and official communications. It helps us trust that we are talking to the right person or company, not a clever fake. Finally, let's consider all the places we use it. When you visit a website and see that little padlock icon next to the address in your browser, that's cryptography at work. It means your connection to that site is secure. Your credit card information is encrypted when you buy something online. Your messages on many chat apps are encrypted, so only you and the person you're talking to can read them. Even your Wi-Fi network at home uses cryptography to stop neighbors from snooping on your internet activity. Without it, the internet would be a much less safe place. It's the invisible shield of the digital age. Now for the really cool science. There are three main types of cryptography, and they each work in a slightly different way. The first one is called symmetric cryptography. This is the simplest to understand. Imagine you and your friend have a secret diary and you share one single key to lock and unlock it. That's how symmetric cryptography works. You use the exact same key for both encryption, locking the message, and decryption, unlocking it. It's fast and efficient, great for encrypting large amounts of data. The challenge, of course, is sharing that secret key safely in the first place without anyone else getting their hands on it. The second type is asymmetric cryptography. This one is a bit more complex but incredibly powerful. Instead of one key, you have two, a public key and a private key. Think of the public key as a mailbox with a slot. Anyone can know where your mailbox is and can drop a letter, an encrypted message, into it. But only you have the special private key to open the mailbox and read the letters inside. You can share your public key with everyone. They use it to encrypt a message for you, but only your private key, which you keep totally secret, can decrypt it. This solves the problem of sharing a key safely. The third type is called hashing. This one is a little different. Hashing doesn't encrypt a message to be decrypted later. Instead, it takes your message and turns it into a unique, fixed-length string of characters called a hash. It's a one-way street. You can't turn the hash back into the original message. Think of it like a fingerprint for your data. Every piece of data has its own unique fingerprint. If you change even one tiny letter in the original message, the hash will change completely. This is amazing for checking data integrity. Websites also use it to store your passwords safely. They don't store your actual password. They store its hash. So, let's review with simple examples. For symmetric encryption, think of the password for your home Wi-Fi. Everyone in your house uses the same password to get on the network. For asymmetric encryption, think of sending a secure email. Your friend uses your public key to scramble the message, and you use your private key to read it. For hashing, think about downloading a large file from the internet. The website often provides a hash. Once you download the file, you can calculate its hash on your computer. If your hash matches the one on the website, you know the file wasn't corrupted or changed during download. Pretty neat, right? So, how does all this science keep us safe every day? It's all about layers. Our digital systems don't just use one type of cryptography. They often use all three together to create a super secure environment. When you connect to a secure website, like your bank, your browser and the bank server start by using asymmetric cryptography. Your browser gets the bank's public key and uses it to safely create and share a brand new temporary symmetric key. This process is called a handshake, and it happens in a flash right before your eyes. It's the best of both worlds. Once that secure handshake is complete and a secret symmetric key has been shared, your browser and the server switch over to symmetric cryptography for the rest of your visit. Why? Because symmetric encryption is much faster for handling all the data that goes back and forth as you click around the website. So, you get the high security of asymmetric encryption to start the conversation safely, and then the high speed of symmetric encryption to keep the conversation going smoothly. It's a clever combination that gives us both strong security and a good user experience. Without it, secure online shopping would be slow and clunky. And what about hashing? It's working in the background the whole time too. Every time data is sent, a hash can be sent with it. The receiving computer can then recalculate the hash of the data it received. If the hashes match, it knows the information arrived perfectly without any changes. This ensures the integrity of the data being exchanged. It also plays that vital role in protecting passwords. When you create an account, your password is hashed, and that hash is stored. When you log in, the password you type is hashed again, and the system just compares the two hashes. This way, the website never knows your actual password. Cryptography is one of the most important tools we have for building a safe, trustworthy digital world. It protects our secrets, verifies our identities, and ensures the integrity of our information. From the simple codes of ancient history to the complex algorithms running our modern internet, the core idea remains the same: keeping information safe. It's a fascinating field where mathematics, computer science, and engineering come together. The next time you see that little padlock in your browser, you'll know there's some seriously cool science making it all possible. Want to unlock more amazing secrets about science and technology? Then consider this your invitation. Subscribe to our channel Nexa for more incredible knowledge. We make the complex simple. See you there.